So we'll continue this afternoon with Carlos's fourth lecture on the study of the nonabelian Hodge correspondence at infinity.
Okay, so thank you very much. So thank you very much for continuing. I don't know, Pranav said I was working hard, but maybe you guys are working hard too. Okay, so what I'd like to do today is, well, so I'd like to continue a little on Donagi Panten for geometric Langlands. And then discuss the structure at infinity. This is my work with Pranav. Lima Kaptarkov, Alex Knoll at the start, and then Fabian Hayden more recently. And so before that, let me just take the opportunity to discuss an important, obviously, main important aspect here, which is kind of common to the two. So we'll take the opportunity to do an introductory thing on spectral curves. So that's going to be, of course, that's important in all of Hitchin's theory. Okay, so let's start with spectral curves. So remember that Higgs bundle. So now let's spectral curves or spectral varieties. So for today, let's let C be a curve. That's a smooth projective curve. So I'll mention what happens in the higher dimensional case also. So now a Higgs bundle let's say a GLR Higgs bundle over C. The theory of spectral curves is much simpler for GLR, as many of you know. It becomes much more complicated in the case of principal bundles. Then you have to go to maybe Cameral cover and stuff like that. But for GLR, the notion of spectral curve is very natural. So if we have a Higgs bundle over C is a bundle and a Higgs field. Okay, so phi goes from E into E tensor omega 1x. The thing to remember is that this looks like a connection operator, but it's a O linear. Okay. Now, how can we view this in a different way? So let's do this in an abstract sense. So we can rewrite this as Tx, a tensor E, mapping to E. And this gives us an action of the symmetric algebra. So this is the relative symmetric algebra, over X. This is in this case, rank 1 coherent sheaf on E. Okay. Oh, sorry, thank you. Sorry about that. Yeah, okay. So this gives us an action of the symmetric algebra on T on the tangent sheaf. Let's just remember this is just a chapter in Hartshorne. A little interior chapter on Hartshorne. It's like one of the easiest chapters to understand in Hartshorne. So many of you who read Hartshorne will probably have latched onto this since it's not all that difficult to understand, whereas as opposed to many other parts. But anyway, so we get a relative spec of this algebra. Which is an affine, which is a scheme that has an affine map. Okay. And there's just an equivalence between sheaves, let's say quasi-coherent sheaves, on this relative spec. Oh, that's just that. is just the same thing as quasi-coherent sheaves on X plus an action of the algebra. Okay. And so in our case, we have this, we have E, right? So because of this, it means that we get, this is going to correspond to a sheaf F, let's call it F, inside here. Okay. So that's just purely formal, just because, I mean, it's like, suppose if we do the case where C is a point, you might say, a module over the ring K bracket T, the ring of polynomial ring, that's the same thing as a vector space plus an endomorphism. The endomorphism being the action of T. We're just doing the same thing relative to C here. Okay. So what does it mean? It means that our Higgs bundle, E phi, so E phi, corresponds to this sheaf F on this relative spec. But this relative spec, in this case, this is just the cotangent bundle of C, the total space of the cotangent bundle of C. Okay. And this is an equivalent. So giving a quasi-coherent, you might say, Higgs sheaf is going to be the same as giving a sheaf on the cotangent bundle. And E is going to be coherent and locally free if and only if F is finite over C, which basically means it's coherent on T star C, and the support of F is finite over C. Okay. And locally free if F is flat, and in fact, that's just equivalent to having no, has no. Of course, F is a torsion sheaf, right? Because its support is finite over C, but being flat means that it has no torsion with respect to multiplication by functions that come from C. So it has no sections. This is really equivalent to has pure. If you have, I mean, a torsion for a coordinate at C, that would be a section supported at a finite point. Okay. So we conclude that that E comma phi, our Higgs bundle E comma phi, that just corresponds to F, which is finite over C and pure dimension. Now, one can actually use that to construct the moduli space. Let me remark, as I kind of vaguely said this yesterday or the day before, but let me say this again. So this was first constructed by Nice-Sophia. But it also kind of makes clear what's called the Bogomolov-Gieseker correspondence. Known as the BNR correspondence. Which says the following thing. So maybe that's stated usually in the case where F has rank 1 over its support. So let's let sigma be the support of F. And let's say, for example, let's say that also sigma is smooth, for example. then F just corresponds to a line bundle over sigma. And sigma is called the spectral curve. Okay, so this discussion is supposed to uniquely determine what the spectral curve means and so on. Let me just go back and recall what this actually comes down to saying, okay? I'm sorry, many of you know this by heart, obviously, but in case of students, for example. What does this come down to saying? This comes down to saying the following thing, that at a point z inside C, in our curve, we have E sub z is just isomorphic to some vector space C to the R is the rank, and phi sub z. So phi sub z, right? It usually goes from E sub z into E sub z tensor kx sub z, right? But if we choose d by dz, choose a tangent vector, then phi sub z, kind of evaluated on the tangent vector. This is just an endomorphism of Ez. So since Ez is just a complex vector space of rank R, this is just R by R matrices. Okay. And as an R by R matrix, it has a spectrum, so we have look at the set of eigenvalues. Okay, so now if you think about this a little bit, since I put the tangent vector over here, that means that if I don't want to talk about the choice of the tangent vector, if I choose a tangent vector, then I get the eigenvalues are numbers. If I don't want to choose the tangent vector, what's the eigenvalue? The eigenvalues are numbers in their element, lambda I of z. Lambda I of z is just an element of kx. Sorry, how did I put an x here again? Sorry. Sorry about that. Right, so in other words, a one form at z. Okay. So the eigenvalues of this matrix are, naturally speaking, they're one forms at the point z. Okay. And then what's sigma? Sigma is just the union of all this stuff. So it's the set of all points of the form z comma lambda of z. Okay. So that should be perfectly clear. If anybody has any questions. And this is, a little lemma or exercise or something. I mean, from what I said here about the Hartshorne, the symmetric algebra, and so on, it just comes out to this at the end, okay? Which is to say, this is just, then that's why it's called the spectral curve, right? This is just the spectrum of the endomorphism phi, right? If somebody writes down the phrase, let's look at the spectrum of the endomorphism phi, and you think about it for a while, there's no other thing that you could possibly come up with as an answer for that other than this. Okay. And so this is called the spectral curve. Now F, let's call this line bundle L here. So F corresponds to our line bundle L. And L is just the same thing. I mean, it's just what you think it would be, which is to say L at the point z comma lambda of z. This is just the eigenspace. This is the lambda of z eigenspace. and saying that sigma is smooth says that over general points Z, we have distinct eigenvalues. Then, of course, something happens, and in fact, indeed, it turns out as we were developing more and more knowledge about this, it turns out to be, of course, a crucial, obviously, aspect of the whole situation, which is that sigma is in general ramified. Let's say it's pretty much always ramified. If genus is at least 2. I mean, if genus is not 2, then it's always not ramified. In fact, for like an elliptic curve, it would have to be a disjoint union of sections, for example. But in that case, the bundle has to split for that reason. And you can, in fact, calculate the, let's see, what's the statement? So, in fact, what's actually true is that, is that true? I think that's true. I think what's true is that if we take pi lower star, let's call this pi lower star of O sigma is going to be O, if I'm not mistaken, C plus KC. No, sorry, TC, I think. And so from that you can actually, because why is that? That's because the functions, since the sheaf F has length R at all the points, it means that the functions, right? Functions on, let's not do some notation, but functions on T star C that have relative degree R in the fiber, this stuff. And that formula tells you can calculate how much ramification you have to have. Okay, so that's the spectral curve. Is it time to do an example or not quite yet? Hello? Well, I said if sigma is smooth. Of course, the general case is sigma is really not it's not necessarily a reduced subvariety. In general, sigma is going to have some nilpotent reduced structure. That's the case where, I mean, if the eigenvalues are not distinct at a general point, that means that sigma is going to have components that actually have some higher multiplicity. And there, of course, the structure is more complicated, so that you can't really say anything very general. I mean, you can say some stuff, I guess, but for example, you can't immediately distinguish in any case the difference between having a rank 2 bundle over a smooth spectral curve or having a rank 1 bundle over a second infinitesimal neighborhood of the spectral curve. You'll distinguish that by whether the Higgs field has whether it's semi-simple or not or something like that. But kind of numerically speaking, you wouldn't be able to distinguish those things. No.
That's algebra structure, right?
No. No, I'm not saying anything about the algebra structure on that thing, just as a sheaf. It just means, I mean, in the case where sigma is smooth, it means, all right, sigma is going to be flat. Sigma itself is going to be flat, not only F, but sigma is going to be flat over C, right? So it means that in each fiber, there's exactly R points. The intersection of sigma with a fiber is exactly R points. And polynomials of degree R is on just a line. Polynomials of degree R, R minus 1, I guess, map isomorphically to their value on any length R subscheme. That's what that says. Okay, are we done with spectral curves here? I'm a little lost. Okay, I think we're done with spectral curves. I just wanted to insist that the fact that a point in the spectral curve is really a point in the base plus a 1 form, which is an eigen one form of phi. Okay. Oh, sorry. Okay, now I realize. Okay, so now what we should do is let's look at how the spectral curve construction interacts with the moduli space. Of course, that's the Hitchin map. Which says, how can we determine? So let's try to make a map from the moduli space of H into the set of spectral curves. Okay. So if you think about it, what's a spectral curve? If you use the formula for the eigenvalues of a matrix, but just relative to the base C, then the spectral curve, sigma. The sigma is going to correspond to the characteristic polynomials. So here I'm cheating a little bit, but so in the general case where f is a sheaf, you can still define a spectral curve by putting multiplicities along each component, which is the multiplicity of that component as an eigenvalue. That defines kind of a unique subspace. I think it's probably the fitting ideal or something like that of the module. And that's not going to see the difference between rank 2 bundle over a reduced curve or rank 1 bundle over an infinitesimal neighborhood of order 2. Those are both going to have a spectral curve in that sense, the order 2 infinitesimal neighborhood. Okay. So by spectral curve, means we count with multiplicity. And then in that sense, a spectral curve is just determined by its characteristic polynomial. Of course, I guess I should have insisted here. Obviously, this ordering of the roots is not unique. And so that depends on your choice of the point. You choose an ordering. As you move around in the base, the spectral curve is going to have monodroming. As you move around in the base, since it has ramification points, as you move around in the base, those lambda 1 and lambda r get permuted. That's like the fundamental thing that happens with spectral curves. So the individual eigenvalues are not well defined, but of course, as you know from linear algebra, the characteristic polynomial is well defined. What is the characteristic polynomial? It's just an element, it's been written this morning, I think, trace of lambda times identity. T times identity minus phi. Something like that. But it's just naturally, so what's it naturally a section of? If you sort of look at this, I think that should happen. It's a natural section of the direct sum. Let's write it this way. It's going to be t to the r plus a r minus 1, t to the r minus 1. Maybe they should say a1, t to the r minus 1, plus and so on. Sorry, thank you. Right, so if we write it this way, then the AIs, what are they naturally? They're naturally sections of C with KC tensor I. So this set of characteristic polynomials, in turn, is equal to, let's call it B, which is direct sum of I equals 1 or 2 up to r minus 1 of, right? This is called the Hitchin base. This is the Hitchin fibration. So from what we said so far, we can see that for a general point, very interestingly enough, as Oscar must know, in the case of real bundles, you can also try to make a map like this, and there's an interesting paper of Laura Shapuznik and somebody else, Nigel, I think, which shows that there's a certain example in the case of real cases where the general point of the Hitchin base, that at least that's in the image, has as its inverse image rank 2 bundles over a smooth spectral curve rather than line bundles. But that doesn't happen in the complex world. Okay. Yeah. Okay. Oscar said Anna Peon's thesis, if you're looking at Anna. Okay, so for in the complex case, for a general point, the spectral curve is smooth. And from what I said here, these coefficients determine sigma, right? Sigma is just, let's not write this down here, but sigma is just the subvariety of the, I mean, this is an equation for a subvariety of the tangent space. Where are we? Where's my spectral curve? Did I say? Oh, sorry, I didn't even say this. I should have said this. Right, I guess I'm not supposed to put it up there. Somewhere down here, we have to note, I mean, from all this, that's what I was saying, but sigma is a subvariety of the tangent, the cotangent bundle of C. That's what all this says. That subvariety, this is just the equation for that subvariety, where T is viewed as the equation of the fiber parameter, and that's why we have this twisting. Okay. So for a general point, you know, in the cases we're interested in, like genus 2 and so on, bigger than or equal to 2, the spectral curve is smooth, and the H inverse of B is a set of line bundles L of appropriate degree on sigma. So it's isomorphic to the Jacobian of sigma. That's in the case GL. Or some kind of prim variety. SL. We actually, when you actually do stuff here, you actually do the case of the group SL, which is you're fixing the determinant. If you think about it a little bit, fixing the determinant, that means that the determinant of the line obtained is pi lower star. Where are we? Oh, sorry, I didn't write that either. Well, okay. Sorry about that. This map, I should write that here also. The map is given by F maps to E, which is pi lower star of F. I knew it. I wasn't done with spectral curves yet. Right, so in particular, it means you take your line bundle, and you take the direct image of the line bundle down to C, and then that's E. And then you want to fix the determinant of E, for example. If you fix the determinant of E, that means you're allowed to take any line bundle up here, but with the property that it's traced down to a line bundle on C is 0, so that's some kind of prim variety. Okay. But in any case, so this is a torus, a complex torus. This is an abelian variety. So now I think, let's hope I'm done now with spectral curves. So now let me get to the geometric Langlands thing. Let's check here. Here. So now there's something very interesting observation was made, I guess probably by physicists and by mathematicians too, maybe a little later, but some occasionally earlier. So I guess this is probably what goes under the term electromagnetic duality in Kapustin-Witten and stuff like that, maybe, or Gukov-Witten or something like that. There's this observation. So this is kind of a philosophical type of observation, basically. So geometric Langlands program, it means we're going to have a group G, and it's dual, and it's Langlands dual LG. And in our case, we're not going to actually work with G's, because as you can see. But in our case, this is like SLR, and this is going to be like PSLR. And we're not even going to work with PSLR. What we're really going to do is work with bundles on both sides, which are bundles that have some degree different, possibly different from 0, which is not the same. So if you take a look at bundles with a fixed determinant, but degree different from 0, that's kind of halfway in between these things. So what we'll actually be doing here is actually those. So, but of course, the theory is supposed to work with the group and the dual group. So for the theory, you would need to really do the principal bundles and stuff. Okay. But for today, we'll be able to skip that, luckily enough. Okay, so now what's the observation? Is that we have, is that the Hitchin base for the group G, when we fix a curve, The Hitchin base for the, and a rank R. The Hitchin base for the group G, oh, I guess, sorry, we have these group and the dual group. Hitchin base for the group G is naturally isomorphic to the Hitchin base for the Langlands dual group. Okay, so now we can look at this. Now we can say M H of G, it has its Hitchin fibration to its base. Let's just call this B. Now we have two fibrations. These are two fibrations that have with general fiber being a torus. You know, a real torus, but which has a complex structure, so it's an abelian variety. And furthermore, part of this observation is that, and this is one, and two, is that at least the smooth fibers are naturally dual. So obviously in a large group, and in the minds of a large group of people, which I probably wouldn't have been one of them at the time, but anyway, but it seems good in retrospect now. In the minds of many people, when you see two fibrations with torus fibers, and they're dual torus fibers, you immediately say SYZ mirror symmetry, right? Okay, so this is supposed to be some kind of case. I guess. Sometimes there's things that would look like a duality, but then people say, no, that's not really mirror symmetry, that's some other duality or something. Anyway, I'm not really an expert on this stuff. Okay, this is supposed to be some kind of SYZ mirror symmetry, and so kind of by general philosophy, it should have some, it should play, this fact should play an important role. Okay. In particular, I mean, this comes from geometric Langlands, right? We took the Langlands dual group, so it should play a role, in particular, in geometric Langlands. So what's the proposal? So there's kind of two versions of the proposal. And I think this proposal, I mean, this was really formally made by Donagi and Panten. In any case, as I was saying yesterday, Thomas Hausel then said, oh, actually I wrote a letter to Hitchin in 1998 or something like that that suggested that we look at something like this. When I heard it talk about by Faltings at the Institute in 2005, I think, or 2006, 2005, I guess, I was thinking, is this something like this going to be true? I mean, but he wasn't exactly saying that, but seemed to sort of say that. But Witten once at the Institute said, oh, by the way, Carlos, you know there's this construction of Higgs bundles and so on in higher dimension. He said, I only know one construction of Higgs bundles in higher dimensional varieties, which is this one. So I think many people have thought of this, possibly many of you in the room also. As far as I know, let me go out on a limb here. I think that really the first place this was put in print, you might say, is Donagi Panten. And in particular, so the first one is called the classical limit. This is their paper. This is a paper of, I'm not sure what year. I think it's in Invenciones. Called major paper. From a while ago. And what this says is they define some kind of classical limit of the geometric Langlands. With kind of classical limit Hecke operators, etc. And they show that, that the classical limit is obtained in the following way. I'll explain. And then part 2 is that, in fact, then they said, okay, maybe if we conjugate by the nonabelian Hodge correspondence, which in this context is really due to Mochizuki, then you might actually get the let's not say full, the non-classical geometric Langlands. Okay. Now let me explain what the correspondence is. It's what I said yesterday, briefly. So remember that geometric the GL here means geometric Langlands. GL, geometric Langlands, what does it say? It says that a local system given an LG local system, let's call it rho, think of a representation on C, we should get and so for your the aficionados, this really means the skyscraper sheaf on the moduli space on lock supported at rho. Because the geometric Langlands, and this is complicated, and there's Geitz-Gory's work which says that it doesn't exactly work like this, but for general points it should work like this still. Roughly speaking, it's O coherent sheaves on, or quasi-coherent maybe sheaves over here, and D modules on the other side. So but a particular example of a coherent sheaf is a skyscraper sheaf. That's why we're just simplifying to a local system. We should get a D module on bun G, okay, which is a rho Hecke, rho eigenvalue for some Hecke operators. So roughly speaking, we're going to have sort of bun G that's right, Hecke. It says if you pull back, you take our D module, let's call it V here. We take V here, and then we take R Q lower star of V. That should be equal to the original V exterior tensor product with rho. And the Langlands dual thing is supposed to make this work. I don't understand this, which is part of the problem with the finishing our work on the question, obviously. But that's the statement that you're supposed to have, okay? But just as a general matter, what does this really mean? It really means if we have an LG local system on C, we're supposed to get some kind of D module on bun G. Then V should correspond to V restricted to bun G stable, which is a D module on the moduli space of bundles, right? And in turn, it should be a local system, right? A D module is going to be a local system. It might be trivial, maybe, but let's hope not. Right. So this is the basic setup here is that if we have a local system, we think of it as a skyscraper sheaf, plug that into whatever kind of geometric Langlands process they're supposed to be. That's supposed to give us back out on the other side a local system So maybe let's draw in the MG without the H is just the moduli space of bundles. Let's see. So the basic thing, so this is where I get curious, which is the basic thing says, okay, if you're given a local system on the curve, then you're supposed to get a local system on this open subset. So can we actually describe what that operation actually does, okay? And it's extremely difficult, at least for me, to find in the literature a description of what the operation actually does in the proofs. So this has been proven by many people, Drinfeld, Geitz-Gorey, Bulinen, and so on. Not to speak of course, obviously all the people who do this in characteristic P and number theory and stuff like that. But it's very difficult to understand what their actual operation is in just these simple terms, right? You can write D modules and stuff like that, very complicated, but just in really simple terms, you take a local system, you're supposed to get another local system. Okay? That's not easy to, at least I didn't find that easy to understand. I think once we do understand it, it should be possible to compare that with the construction we're proposing here. But I think the construction that, the Donagi Panten are proposing here, nonetheless, even if we say there exists already a construction, it still has a merit, as we'll see this is an extremely natural construction. So the question would be, how can we find the Higgs bundle? The Higgs sheaf, maybe, on U corresponding, let's say, on M, comma, and divisor. It wouldn't make sense it wouldn't make too much sense to ask for a formula starting from the local system and going over to the Higgs bundle, right? Because we know that it's very transcendental. The correspondence going from a Higgs bundle to a local system is very transcendental. So we're not going to have a formula that goes from rho to this thing, to V. But we could, this was what Donagi Panten were saying, we could imagine having a nice formula starting from the Higgs bundle corresponding to rho and getting the Higgs sheaf there. So let's just analyze a little bit what the Higgs bundle corresponding to rho is going to look like. So this thing is going to correspond to a line bundle. Let's call it LL. That's not maybe great notation, but a line bundle on the spectral curve. Call it sigma L, maybe just sigma, which is the spectral. Right. Just by what we said before, Higgs, for a general point, so if B is general. B is HL of rho. And this construction is really, for the moment in any case, it's only working in a couple of examples for one thing, but also completely assuming that we're at a general point. Okay? So the spectral curve is smooth. We have a line bundle on sigma. Well, which is a point in HL inverse of B, right, which is some kind of prim variety. Right? So a Higgs bundle on this side, we'll have a point here of our spectral curve. The Higgs bundle is going to correspond to a line bundle here, which corresponds to a point. In this variety. And what does this whole stuff say here? This says that the fiber of the Hitchin map here is the dual abelian variety of this one. So this observation says that says that, sorry, this is, I know. This board looks a lot like this board, sorry. Could probably even have gone without erasing it, but let's not do that. Right, so our point, let's call it y. Oh, well, let's see. Let's call it y again. This corresponds to a line bundle on the H inverse of B. This is an abelian variety, which is again some kind of prim. Somebody was asking yesterday, what's the relationship between these two things? So I mean, probably in many cases, the prim is going to be principally polarized also, I think, so just the same. But kind of functorially speaking, so to speak, our point here is a point here, so it's going to correspond to a line bundle, L, on the other side. And then the idea is that we can just, so let's call this y0. Let's just try to project that down to here. I guess I'm calling that var pi. But then noticing that, so we have y0, which is this H inverse of B, which is kind of, roughly speaking, contained, rationally speaking, inside the cotangent bundle of M. As we said before, the moduli space of Higgs bundles is, roughly speaking, the cotangent bundle of M. We'll see in a minute the difference. And so this is going to be BNR data, so L over here. So Donagi Panten say, to define as think of L as BNR data, with this as covering, to define a Higgs sheaf, var pi lower star of L, with its natural, so it has a tautological form, right? The fact that this is roughly contained in the cotangent bundle of M means that it has a tautological form. And this is the class, so in the classical limit this works. And then two, so this was Donagi Panten for P1 minus 5 points. I wouldn't say it's their most recent, because you never know, but it's one of their recent archive papers with a kind of long paper. It's got lots of calculations, partly because, well, you have to do lots of calculations anyway, but partly because you have to do parabolic structures. And then current work in progress with me. I just steal a joke from Hirschhorn-Dwyer-Kahn. Current work in what we like to think of as progress, right? That's not me. That's Dwyer. That's Dwyer, Hirschhorn-Kahn. Okay, but anyway, current work in progress with them treats the case of genus 2 curve. But let me just say, we're still kind of having trouble with the Hecke. So the Chern class calculations look okay. We're still having trouble with the Hecke eigenvalue condition. Should be stopping this segment a little.
What component degree
Yeah, so I thought I would explain that. This is a beautiful story, and also goes back to, once again, Professor Narasimhan's paper with Ramanujan. So let me just take 10 minutes to explain. So let me not do any kind of like calculations or anything. But let me just explain whether the moduli space is in this case, as many of you know, obviously. Just kind of briefly, what's the setup? So in this case, so let's discuss this case. So R equals 2. So vector bundles on a genus 2 curve if we look at the moduli space with determinant equals OC, that's P3. That's P3. And the moduli space with determinant equals, so let's say OC of P, that's the easiest choice for us, for P is a Weierstrass point. See, when you're taking, if you're taking odd degree, and you want, but you still want to fix the determinant, then you can choose whichever one you want it to fix. And since there, I mean, sometimes you can, it can be useful to take the hyperelliptic involution, as I think then did the general case. So this moduli space is explicitly described for hyperelliptic curves of G. But just in our case, but we're not doing that for the geometric Langlands yet in any case. Just in this case, this moduli space, this is an intersection of two quadrics in P5. Okay. And then the Hecke relates these two. So there's going to be a so it's a little complicated. It's roughly speaking, it's not really M1 cross C, there's a twisting. So this is part of the reason this is complicated. If you think about the natural Hecke isomorphisms, the Hecke is not going to fix the determinant. You're doing a Hecke, at a 1-point Hecke, that's going to give you a bundle with determinant equal to that point. So it's not going to be really this one. So it's this is some kind of twisted. But the point is that the Hecke correspondence, I mean, you can write down a Hecke correspondence that relates up to this question of the determinant, that relates the two pictures. And that's the thing that we're doing that as kind of Langlands duality. So I don't know, I mean, this is more Ron and Tony's, just the incidence correspondence, yeah. I think so, yeah. Okay, and so, but let me just finish by showing you some kind of the geometry that's coming into play here. So this Higgs bundle, so what's the work you have to do? So the Higgs sheaf needs to have a parabolic structure on what they call the wobbly locus. Which is non-very stable bundles. Let me not even give the definition, but let me just draw the picture here. In the nilpotent cone, of the Hitchin moduli space, then the moduli space of bundles is the bottom component. And there's some other fixed points. And the wobbly locus is all of the things you get by flowing downward from a fixed point in all possible directions and hitting M. Okay. This is W. So in a nutshell, that's the wobbly locus. The wobbly locus is the places where the other components of the nilpotent cone join on to the basic one. Okay, so that's W. So let me just finish this segment by just explaining what is the wobbly locus in these two cases. It's kind of interesting. So in the case P3, this is the Kummer. There's a Kummer surface inside P3. This is a P3, which is like a space of sections of a theta line bundle. There's a Kummer surface associated to the Jacobian of C inside P3, union 16 what are called trope planes. And in some sense, the Kummer is not really part of the wobbly locus, so this might be one of the reasons why it's a little confusing. The Kummer is not really part of the wobbly locus in the sense that the Kummer is the place where the moduli space is singular because there's polystable bundles. Okay? So the Kummer thing here, it's actually sitting out here, but it's the singular points. But it doesn't really have an upward going, flowing thing. It's just sort of sitting out there by itself. But actually, so there, in this case, there's a beautiful way of resolving this problem by going to a double cover. We're calling this X prime. Which is parabolic bundles on P1 minus 6 points. And this was observed probably first by Goldman, or maybe by other people, but, and then used by Victoria Hu and Frank Loret. And why is it a double cover? Because if you have a vector bundle on a genus 2 curve, if you have a rank 2 vector bundle on a genus 2 curve, it has to be anti-invariant, invariant by the hyperelliptic involution. When you do the hyperelliptic involution, you have to get back to the same bundle. Okay? And so it should descend to a bundle on P1 minus 6 points with 6 ramification points at the ramification points. But if you think about it a little bit more, you understand that there's two different ways of descending it. Because to descend it, you need to choose an isomorphism of E with sigma star E, and that isomorphism has to satisfy that when you square it, E to sigma star E to sigma star E, which is E, you're supposed to get the identity, okay? So there's a choice, but if you multiply it by -1, then you again get one whose square is the identity. So there's two possible choices. For any bundle here, there's two possible choices of a lift. I mean, this is why it's confusing. We're lifting in the moduli space, but that's actually descending the bundle, okay? There's two descents of the bundle down to here. So the moduli space of parabolic bundles on P1 minus 6 points, that's a double cover, and that removes the Kummer thing, in fact. We use that in our calculations. And so let me just say that this is called Kummer's 16-6 configuration. Maybe you guys in India know this saying more than we do in, like, France, for example. As I was going to St. Ives, I met a man with how many wives? 7, thank you. As I was going to St. Ives, I met a man with 7 wives. Each wife had 7 sacks. Each sack had 7 cats. Anyway, kits, cats, sacks, and wives. How many are going to St. Ives? This Kummer 16-6 configuration is a little bit like that. It has 16 planes and 16 points. And each plane has 6 points. And each point is contained in 6 planes. You see the analogy, right? Anyway. Sorry?
Double sixes, Indians would love. There's something called double sixes.
Yeah.
Sixer is something very important in cricket.
Ah, okay, oh, good, even better. Anyway, the 16 points are the singular points of the Kummer, okay? Anyway, so that's kind of fun. And the plane, so what's the problem here? The problem is that the trope planes, these make a tack node with the Kummer. Luckily enough, when we go over to here, we get normal crossing. But let me just finish by mentioning the other one. So in the other one, I was trying to figure out this calculation. Might have made a slight mistake, but in the case of odd degree, there's a curve C bar, which is a 16-to-1 double cover. Maybe I should just say that the map in our case, our map from Y0 from our thing, this is 8 to 1. So the Higgs bundle is going to be a rank 8 Higgs bundle. There's a 16 to 1 double cover, étal. And the fixed point set in MH is, it's M union this C bar. So the picture looks like this. In this case, so there's a map from, but the downgoing normal direction has 2 dimensions here, so there's a P1 of choices. So it's C bar across P1 mapping, and this is actually, it's actually a product, mapping to M. The image is the wobbly locus. But unfortunately, W has, in this case, has nodes and cusps. So even to make the calculations for the parabolic structure, in the case of nodes and cusps, that actually took us a long time. We kept getting the wrong answer and so on. We finally think we got the right answer because it comes out to 0, shall we say. So what's the overall scheme is we take a line bundle L on Y, which is a blown up of Y tilde, of Y0. The blowing up locus is actually, in this case, it's C. We take the spectral curve across this C bar, and that's C hat, and this is actually blowing up C hat. Then this makes the map well defined. We have an exceptional divisor here. Sorry. Okay. And then we take, so we really take L0 of, I think, E of the exceptional divisor, and then take this var pi. That's going to be V. Then you put a parabolic structure. Then it turns out that it has a logarithmic Higgs field. It's logarithmic because, you guys might have been complaining. Where is that? I guess we erased it. Yeah. It's logarithmic because of this dotted arrow here. This Y0, and even if you blow up to get Y, you don't actually get a map to the T star M, but you do get a map to T star log. It's actually kind of halfway between. It goes to T star log, but it goes, all the new stuff goes to the origin, but in a ramified way. Anyway, so you do work a little bit. You define a parabolic structure following Donagi Pantev's kind of general yoga. Has a logarithmic Higgs field, and then if we check C1, if we check that the delta equals 0, so this is the proposition. And this is the main question is how to choose all this data, including the parabolic structure, so as to get delta equals 0. That's not in general easy to do. You can see it's not easy because you have the Bogomolov-Gieseker inequality that says it's greater than or equal to 0. So getting it down to 0 is the hard part. Okay. The parabolic structure is along W. Yeah, good question. Parabolic structure along W. And in this case, so it's a little bit more tricky. In this case, it's actually the parabolic structure along the Kummer, which comes from the fact that when we go to the double cover, which is branched over the Kummer, it's actually not a parabolic structure. But down here, it has a parabolic structure with weight 1/2 along the Kummer. And the fact is, if our calculations are correct so far, we don't actually get a parabolic structure here. So it's actually unipotent monodromy, right? You have logarithmic Higgs field, which is unipotent. But it doesn't, it turns out you don't put a parabolic structure here. That's maybe not completely 100% sure, because in the more general case of parabolic bundles, then if you varied the weights a little bit more, you would put various parabolic structures there. So we claim to be able to do this, roughly speaking. As I said, it's not really written down 100%. Then what we're trying to work on is to try to show that the resulting local system satisfies the Hecke eigensheaf property. That's more complicated because for many reasons, but notably because of things like these cusps or these tack nodes. It's not a normal crossing divisor. So you have to do something.
If you want to get the unipotent, could you just add a Higgs field
Well, I mean, you can't really just add a Higgs. I mean, it's a Higgs field that happens to have a pole. I mean, it has a logarithmic pole. Yeah.
Oh, okay.
Yeah, it's a Higgs field that has a logarithmic pole, which is where the residue is nilpotent. But if you did put a parabolic structure, you'd use that nilpotent residue to make a strictly parabolic structure by putting that subspace as a parabolic weight subspace. But if you put zero parabolic weights, then it's basically matrices, that have an eigenvalue close to 1. If it sort of degenerates, then it can degenerate to a unipotent matrix. I mean, that's what's going on. Anyway, so let me just finish that segment of the talk. So I have 24 minutes to go. So yeah. I mean, I'm not explaining here what you need to do. That would take another hour or so, or two. I'm not explaining what you need to do in order to, you want to calculate the delta, but you only know the calculation of the delta in the case of normal crossing divisor. So you have to calculate what the delta would be if you had cusps. I had a student, Chadi Tyre, who wrote a thesis about that. But you don't actually need to use Tyre's thesis here, luckily enough, because it turns out the parabolic weight is 1/2, even in this case. And when its parabolic weight is 1/2 on a cusp, you can actually go to a finite cover, which is ramified of order 2. This is the what's it called, the conifold transition or something like that, right? C2 mod S3 maps down to C2. The branch locus is the cusp. It's a Galois cover with order 2 ramification. So if you have a parabolic thing on the cusp with weight 1/2, if you pull it back to the smooth variety, you get if you put unfortunately, inverse image is 3 crossed lines. So if you take any parabolic structure on the cusp and pull it back, you'll get a parabolic structure on 3 crossed lines, which Chadi kind of looked at in his thesis. But in this case, if you take a parabolic weight 1/2 and pull it back, then since it has ramification of order 2, that 1/2 goes away, and upstairs you don't have any parabolic structure. So then it's just smooth, and then you can do the calculation. That's the rough answer. Okay, so now let's do the next. Okay, let's check that one off, so to speak. Right, it's good to. I've got the talk, so I can do that if I want. Right? Okay, so now let's look at let's go to the next section, which is behavior at infinity. So this is work with Panov, Ludmil, Alex Knoll, Fabian Hayden. Fabian wasn't really on the papers of the stuff that I'll be able to talk about today, just the starting point. We're working currently with Fabian on stability conditions and stuff like that. But it has to be said that Fabian was present while we were doing the whole work. I think Fabian would agree that Fabian made a lot of comments which, led us on the way to the right direction anyway. So he's kind of morally in the project from the start, in fact. And so, well, how does this compare with the previous one? So in this previous situation, we've been very concerned with taking the Hitchin fibration and pushing everything down to the nilpotent cone, right? So that's like a visible thing of the Hitchin fibration. So lots of people study it and stuff like that. So you can take everything, push it down to the nilpotent cone. And we're looking inside the compact subspace of the moduli space. And now here the question is, okay, what happens if we go back in the other direction, basically? Okay. So the first observation is that note that we have the nonabelian Hodge correspondence says we have the Hitchin moduli space is isomorphic to the Betty moduli space, which is representations. Which is also isomorphic, I didn't talk about this, but to the Dram moduli space, which is vector bundles with connection, okay? And this is complex, this is not holomorphic. This is complex analytic, but not algebraic. And in fact, so well, Hitchin says more precisely, I'm going to get this wrong, it says J. Oscar, you can correct me if I'm wrong. I think this is I and this is J. Is that good? So we have a hyperkähler triple here. So the M, the kind of generic M, which is all these things the same, has a hyperkähler structure. Kind of maybe a little bit unfortunately, I would say, but so there's a lot of the theory. So the theory we heard this morning by Emanuele about hyperkähler manifolds, so those are compact hyperkähler manifolds. These are non-compact, okay? So what I want to say is that M Betty is an affine variety. So it's non-compact. Okay. I do think it would be good at some point in the maybe far future to have some kind of understanding of the relationship between these compact hyperkähler manifolds and these non-compact ones. I think Huybrechts maybe has some comments about that. But. Anyway, so these are non-compact ones, so they kind of have a different flavor, I guess. They're still pretty rigid, but maybe a teeny bit less rigid than the compact ones. Okay, so M Betty is an affine variety, so it's non-compact, so the other ones have to be non-compact also. We can also see that MH is non-compact. Right, we have the Hitchin fibration to the base, which is just C to some power, right? So that's non-compact. And so a kind of basic question is, how do these compare? Well, so let me just make a comment. What are we doing for time? Okay, so let me make a comment about compactification. About compactification. Okay, so for M Betty, the mapping class group acts in a bimeromorphic in an algebraic way. And if you think about this a little bit, you'll understand that there's not going to ever be a invariant compactification. So there's no canonical compactification. In other words, you'd have to choose like a set of generators. If you choose a set of generators for the fundamental group, for example, then the M-Betty can be embedded into some space of matrices. And then you can use like maybe wonderful compactification or something like that. But you have to choose a set of generators. So, but what I'm about to say is obviously cheating in a strong sense because this M-Betty does not depend on the complex structure, right? But if the MH and the M DRAM depend on the complex structure of C, right? And so you might even think of whether my questions about, asymptotic stuff you might even be able to sort of make a relationship between these things. But in any case, choosing this complex structure is a little bit like choosing the set of generators for the fundamental group here. And so from that, and then they have, given that they have a complex structure, then you get a canonical compactification. How can you do this? Well, one way is to define M Hodge is the moduli space of lambda E nabla. We just do this. I mean, many of you know this already. If you don't, you can look it up or something if you want. But, so the point is that these two spaces, Higgs bundles and vector bundles with connection. I mean, I'm sure if you hadn't seen this before, you obviously have been asking yourself that question: what's the difference between a Higgs field and a connection? Well, it's that a connection is a one connection and a Higgs field is a zero connection. You can interpolate those between those with lambda connections for any parameter lambda. But of course, the M Hodge of lambda is isomorphic to M Hodge of 1, which is equal to M Duram for any lambda different from 0. And M Hodge 0 is MH. Right? So this is exactly an example of what Dan was talking about. We got a filtration. In other words, we get a family of spaces parameterized by A1, the stack A1 mod GM, which is Daniel's statement. Right? So we get a filtration in the category of scheme, not projective, but just schemes. Okay. And this is you might say possibly my contribution to the subject maybe is to call this. I mean, this is just nomenclature, right? But to call this the non-abelian Hodge filtration. I should say this was defined by Deline. I mean, this was suggested by Deline. Deline's letter was very funny. He said, oh, Witten was explaining to me his view of Hitchin's construction of the hyperkähler structure, and here it is. I'm not sure. I guess Witten probably would have recognized a little bit of that. Probably not a lot, but anyway. So what I wanted to say is that M Hodge of C union M Hodge of C bar, this is equal to the twistor space of M with its ijk. I should just say that. I mean, let's not get into this because we're out of time here. But why did Deline suggest this? He suggested this as a construction because it doesn't seem all that interesting as a construction, at least at first sight, because it's just it's a family that has two different spaces, which look like they were a lot related anyway. And you would say, I mean, just on a very birational level, this looks like this is like the cotangent bundle of the moduli space. This looks like a torsor for the cotangent bundle of the moduli space. So just thinking in that direction,
What was C-bar?
C-bar is the complex conjugate. It's not the same as the other one. It's the complex conjugate curve. Actually, writing down this isomorphism is extremely confusing, and I'm sure I've gotten it wrong in any places I have actually written it down and so on, so let's not do that. But this is called the Deline, we'll call this the Deline gluing. I mean, it's, we're gluing over M Hodge restricted to C star, which is isomorphic to M Betty cross C star analytic. Right, these families are trivial. Right, this family is trivial over the complement of the origin. If you trivialize it, you just get M Duram. Then you apply this M Duram isomorphic to M Betty. M Betty of the curve is isomorphic to M Betty of the complex conjugate curve. So there's something going on here, right? Isomorphic to M Betty of the complex conjugate curve. Then we can just go back in the other direction. That gives us our gluing map. Homework exercise, Dan. I'm sure you can figure this out much better than I can, okay? No. I mean, any curve over the complex numbers, just take the complex conjugate of all its coordinates. Be they whatever numbers they are. That's why, but of course, it's extremely confusing. I mean, the first place I got confused on this subject, I should say, was in Griffith's graduate course about Hodge theory. He had, you had complex conjugate, and you take a complex vector space and take the complexification of the complex vector space. You have two different complex structure operators, and so I mean, this whole Z mod 2 thing is extremely confusing. So let me just on the subject put out you guys like to say, you heard it here first or something. But I mean, I've said it to people in private, but I think this might be the first time I say it on film. So just going on a total limb here. So all this stuff with Z mod 2 and stuff. And right, in the archival theory, you sort of see Hodge theory as being at infinity. Is there some kind of dual picture of Hodge theory which was at the prime 2? So is it possible that arithmetic geometry over various prime, you always say P equal different from 2, right? Is it possible that arithmetic geometry at the prime 2 has really special properties which would make it sort of dual to Hodge theory and something like that? Anyway. But be that as it may, this whole Z mod 2 Galois group stuff is extremely confusing. But you can actually do this. This does seem to be true. And in fact, so the question is, why is that really? I mean, we know that we have the hyperkähler structure, and so we know we have a twistor space. The question is, why is that the same as the twistor space? Anyway, so that's kind of the philosophical setting for this thing. But for our purposes, we can just look at, let's just take M Hodge minus H inverse of 0 inside the MH part, and quotient out by C star. Okay, so C star acts on M Hodge, right? T times lambda E nabla equals T lambda E T nabla, right? If you multiply a lambda connection by a number, you get a T lambda connection. So C star acts on this space. And this is like just constructing projective space, right? If you're going to construct projective space as a compactification of affine space, you could do it this way if you wanted to. I mean, it wouldn't be all that great a construction, but I mean, it's the same construction, but I mean, if you call it C to the n plus 1, you call it C to the n cross C. Then do exactly this. So you take C to the n plus 1 minus the origin, divide by C star. You exactly get a compactification of C to the n, right? The same principle here. This is a compactification. This is an M de Ram bar. And I think this is maybe Alexander Schmidt. Did the same thing for Higgs bundles. If we just take MH cross C minus H inverse of 0 inside comma 0 on C star. This is a compactification of MH. And if you work a teeny bit more, but let's not do that. If you work a teeny bit more, you can actually make these compactifications fit into a lambda compactification family, of which they're all isomorphic, which degenerates to this one. So this guy degenerates to this one. I mean, along this degeneration, this degeneration, the compactification also degenerates. So I think I just have time to rapidly explain the setup. So this compactification stuff, what does it tell us? It tells us that a typical curve going to infinity is going to give us a spectral curve. And I think that was kind of known actually even back to Liouville or something. People kind of knew that if you had a degeneration of differential equations, you were going to get something that looked like a spectral curve. Okay, so a curve in either MH or MH bar or M de Ram bar that's transverse to infinity looks typically like, let's just put it this way. So this might depend on T or something. So I'm putting T going to infinity. I mean, right, a curve in the coordinate 1 over T. So T should probably be like 1 over H bar or something here. Sure, it certainly is 1 over H bar, but anyway. A typical curve, what you can see from this compactification, just roughly speaking, in our 6 minutes and 35 seconds that are left. What we can see, what's the meaning of this compactification? It tells us that a point in the non-compactified variety, right? A point that's close to infinity in the non-compactified variety, there's a lemma here, which is that the orbits of these points all go towards, all have limits in the 0. There's like a properness of the Hitchin fibration, but for the M de Ram, which even though the Hitchin fibration doesn't exist, but the orbit of a point goes down to here. So any particular point is going to go down to typically either a vector bundle or a fixed point. But if you take a little section like that and push it back by the C star action, then that's going to go to something over here which goes off towards infinity. Right? So if we take a little section like this, which is approaching a point that's the point with Higgs field phi1. Okay? This point here is going to be E comma phi1. Right? If you take a little section like that, the approach is E comma phi1 and then push it back by the C star action. That's going to be something that goes off to infinity. So that's a typical thing going off to infinity. Just kind of the general question is, what's the relationship? So what does the monodromy do in this case? And so like one basic answer so a basic answer is as follows. This is what I'll finish with. This was in our paper with Pranav, Ludmila, and Alex Knoll. We did this for the case of the DRAM, and then Takao Mochizuki kind of filled in one of the steps that we needed in the case of the Higgs thing. Which says that there exists a harmonic map to a building. Not the same H, I guess, but we're calling this H. There exists a harmonic map to an R building like that, such that the distance from H infinity of P to H infinity of Q for 2 points on the universal cover. Sorry, this is C. The universal cover of C. The distance is equal to the Lyapunov exponent. Which is the limit as this thing depends on a real direction, okay, of like 1 over t times the log of the norm of the monodrome of the transport from P to Q. Is this correct? So it tells you how big the monodromy is getting. And so I should say this is like Thurston theory and so on, and Morgan, Shalin. Should probably say Richard Wentworth also. Other people, I mean, sorry, anybody who's looking here, I did that too. The building is a tree. And the E comma phi1 if you go to low-dimensional topology talks, you've undoubtedly heard about some relationship between quadratic differentials, measured foliations, and so on, that type of thing, and maps to R trees and so on. This fits into that setup. But you can do this in more general. And so maybe I should say the key point here. This was actually this part was really n power, in fact. So what we did is we showed that the differential of the harmonic map is equal to the set of the spectrum of phi1. So in other words, it's the spectral curve, but the real parts. So let me just stop here by just mentioning that, so just look this up on the web. So like Matsuo Swoboda Weiss-Witt and Laura Fredrickson. I should mention Andy Guyot-Moranicki here. I don't have time to say how that worked, but this is related to Guyot-Moranicki. You can look in our paper. So they have a vast theory that says how to describe the HK metric. Let me just finish this phrase. At infinity. Kind of by referring to the Guyot-Moranicki's theory. And I think Fredrickson, Mazzio, Swoboda, maybe in one of the two W's, had a preprint this fall, for example. But this is an active area of study, is to maybe there are results so far in the case where the spectral curve is smooth. So there's a big question of what happens when the spectral curve acquires nodes, for example. Okay, so I'll stop here.
Questions? Comments?
So the duality you were mentioning in the second part of the, is there a shadow of that at infinity? Or
I think that would be an excellent question. In fact, we're definitely not advanced enough to treat that question. But yeah, I think there's obviously going to be a question, which is, suppose my spectral curve now goes off to infinity, then my local system, my D module downstairs is also going to go off to infinity. Like, what's the relationship between those two? Yeah, but I mean, we don't have anything to say about that.
So what is this building? How is it related to the curve or its universal cover? That building?
Well, then the building is really more related to the group. I mean, the dimension of the building is like the rank of the group. Okay, so let me just, at the risk of taking a little extra time, but right, if you have a representation from gamma, which is pi 1 of c, if you have a representation into, like, say, SL R of QP, right? Then it means that gamma acts on the classical Brouhat-Hitz building. And so we could look for a Gromov-Schoen. I'm not sure, Panav, if we actually proved that this harmonic map was the Gromov-Schoen harmonic map, but let's say, roughly speaking. Right. And it's worth thinking, it's worth thinking about this case, right? If you have a map from gamma into SLR of QP, which doesn't map into a compact subgroup, then that acts non-trivial on the classical Brouhat-Hitz building. And Gromov-Schoen theory should work pretty well there because it's not an R building or anything. I mean, it works also in an R building case, but this is just a simplicial building. So you just take a harmonic map, an equivariant harmonic map, and that's supposed to be that harmonic map, essentially.
Could you again describe the compactifications of
well, let me say this. Let's put this over here. Let's put it this way. What's the divisor at infinity? So M Durand bar. Let's do M Higgs. Okay, this is going to be the easiest to see. You can pretty much do this anytime you have a C-star action on something. That's because I mean, right, you've got this stuff. This H inverse 0 is compact, right? But if you have a point here that goes off to infinity, if it's going off to infinity in its C-star orbit, then up here you put the point, which is that C-star orbit, but as considered as an orbit. I mean, which you can write down precisely that construction in the following way. It's it's MH cross C minus the nilpotent cone in the 0 fiber divided by C star, but that does exactly that. anytime you have a variety with a C-star action, so you need some kind of properness. You need to know that the T goes to 0 limits land in a compact subvariety. Then if you sort of add points corresponding to all the T goes to infinity limits, pretty much every orbit corresponds to a point, basically. So probably why you're looking a little dubious here is it's true that this has some certain structure. This is actually an orbifold. Because you might have points here. I mean, by definition, a point is not going to be a fixed point. A fixed point has to be down here. But it could be a fixed point of a finite subgroup. So you're going to have orbifold points here. Those correspond to what are called cyclic Higgs bundles. Cyclic Higgs bundles. You can have a Higgs bundle, which is a fixed point of a finite subgroup of C star. And then the point here is actually an orbifold point at infinity. So this compactification is really an orbifold compactification.
So you said there's no canonical compactification, but so there is Perot's compactification, right? So in what sense do you...
Very what? Very smart.
there's Perot's compactification of the character variety.
What I mean by I should have said, by an algebraic variety. Yeah. By compactification, for me, that means an algebraic variety, right? And we're doing algebraic geometry here, so. There's no canonical compactification as an algebraic variety. If you start, I mean, what that amounts to saying is it's pretty much similar to the Zariski space of valuations, right? I mean, you can like compactify anything you want by just putting the space of all possible valuations at infinity. You can put that at infinity. Or like you embed it into its Berkovich space and you take the closure or something like that. I mean, you can get a compactification that way, but it's like this gigantic thing with like zillions of different valuations and stuff.
I just wanted to mention that because this thing can be interpreted as matching up points in the one compactification with Perot's compactification.
Yeah, okay, yeah. I think that's, so I guess that's what Wentworth does in the case of trees, if I understand correctly. Yeah.
Any other questions or comments? If not, let's thank Carlos again.